see a peak here above, at 3080. Okay, and to the trained eye, and that will be yours sooner or later, you'll look at that and say, ah, there's got to be a double bond, at least one double bond in this structure. Okay. We also see the carbon-carbon stretch here about 1642. Okay, and we don't see carbon-carbon stretches generally for single-bonded carbons unless they're polar things attached to them.
What would be the main difference if it did have multiple bonds?
It would tend, this probably wouldn't be affected much. We may see more peaks out here, but what we would definitely see is this thing being shifted down here, particularly if it was conjugated. Yeah.
So there's basically no way of us knowing that it's a one hexene, right? Just by looking at this.
All you could surmise from looking at this is say, oh, there's a double bond in this thing, because you've got two kinds of evidence for it, but you couldn't really go a whole lot further.
Would you know that it's terminal?
No. No.
And the stuff they're showing us down in the, what, the 14, 15, 16 down there, we're not, I mean, is that?
Yeah, the fingerprint region you're not going to really look at. This is not in the fingerprint region. 1642 is up there where you'd look to see if you've got a carbon-carbon double bond.
So that's just verifying what we see up there in the, above
Right,
the 3000.
but notice that even if this double bond were located deeper in the chain, there would still be hydrogens attached to it, so we'd still see this guy here. Unless that carbon is completely attached to carbon or any chlorines and other things, you're going to see that stretch.
What would you answer the question if you had more than one double bond?
And if the double bonds were isolated, what do you mean by that?
Like if you have more than one double bond, you want to know what you're considering.
Yeah, but if the double bonds are isolated, that means they're not conjugated. They would be probably just like this.
Okay.
But if they were conjugated, this might be down here around 1620 or something instead of 1640. It's a subtle effect, but the trained eye would pick up on that. Okay? So you can see multiple double bonds if there's conjugation going on. All right? Alkynes. Here is a terminal alkyne where we've got the triple bond on the end, and notice that in order to have a hydrogen attached to a triple bonded carbon, has to be on the end. In other words, a triple bond between carbons. In the middle of the chain, there's no place for a hydrogen to attach. And so in this particular case, look at this right out here, 3313, really strong and sharp band. That's a dead giveaway. That's in the same region where we might see an alcohol, but is that how alcohols look?
Mm-hmm.
No, they don't. They're more broad. And so we look at that peak out there, and that strongly suggests we're talking about perhaps an alkyne. The intensity and its position and its sharpness. Here's the carbon-carbon band, and it appears, and this is a moderately, well, I would say not quite medium strength, but it's a nice sharp band, about 2119. Notice that if the triple bond is internal, in this particular case, it's right in the middle of the molecule, this thing disappears entirely. There's just not enough polarity associated with that carbon-carbon triple bond that you can show. And notice that this guy disappears also. So if we were looking at this spectrum, there would be no evidence of an alkyne present in the infrared, even though it is an alkyne.
We'd think it's an alkane.
Yeah, you may very well think it's an alkane if you don't have any other evidence to the contrary. Other evidence would be NMR or mass spec or something else. Okay. Now, besides the carbon hydrogen stretch, there are oxygen hydrogen and nitrogen hydrogen stretching bands, and these are usually pretty diagnostic. They're both out around really between about 32 and 3,500. But they look very different. The alcohol stretch is very broad, and it's anywhere from kind of a moderate to weak intensity to strong. Amines are in the same region, but they have a broad band with a spike on them. If I've got a secondary amine, this will appear as a single spike. If I've got a primary amine, it'll appear as a pair of spikes on top of a broad peak. Tertiary amines, because they have no hydrogen attached. What do I mean by tertiary?
Seems a tertiary carbon.
Yeah, this nitrogen has 3 carbon groups and no hydrogen, so that band will be absent in the tertiary amine. Here's an IR of 1-butanol, and you can see the OH stretch is very intense. Now, students will often get concerned about the intensity of this band. It varies pretty dramatically from alcohol to alcohol. And in this particular case, the alcohol peak is maybe the 3rd or 4th most intense peak. In the spectrum, sometimes it's not. Why is the band broad? In other words, one of the characteristics of the alcohol band is the breadth of the band. Why is it?
It must absorb a lot of frequencies or something.
Hydrogen bond. Same thing. And we were all sort of striking at that concept from different angles. Consider an alcohol from that perspective. So here I've got an alcohol. And here, let's bring another alcohol in here. Now I got this hydrogen bond here. As this hydrogen bond forms, this bond weakens. Okay, and so the strength of the hydrogen bond is manifested inversely in the strength of the covalent bond holding the oxygen and hydrogen together. So because I've got hydrogen bonds at varying strength, the oxygen-hydrogen bond varies also. And because of the hydrogen bonding, we see a range of energies that, whereby this thing absorbs. Now, let me ask you a question. What if I had a nice, sensitive instrument and I could dilute the alcohol in a solvent, okay, that doesn't absorb in the infrared, and there are such solvents, so that the molecules are so dilute and so far apart they don't have an opportunity to hydrogen bond? What would you expect?
It'll sharpen.
Generally, this thing sharpens up. It becomes a sharp peak like everything else in the IR. That's good, strong evidence. In fact, that's the evidence. It demonstrates that the broad band is due to the hydrogen bonding effect. If I simply dilute this and then run the sensitivity instrument up, spectrum looks the same, but the alcohol peak sharpens up because the hydrogen bonding effect is diminished. Does that follow? Okay. Here's an amine. This is a secondary amine with a single hydrogen on the nitrogen, and we see a single spike on kind of a broad up. The amine is also hydrogen bonded, not quite as strongly, and so we see a generalized effect. And then, but because some of the amines are not as strongly involved in the hydrogen bonding, you'll usually see a spike for each hydrogen present. And so amines often look kind of ugly, and people will maybe run their infrared again because they're thinking they've done something wrong, because it doesn't look like what they expect to see. Normally not. How would you know if you have an amine?
Off of what?
Mass spec would give you some evidence, but they smell terrible. Like usually, if you've got an amine and you're working with it, they have a terrible odor. The best ones smell about like ammonia, and the worst ones smell like rotting flesh. Normally, if you have an amine, you'll know right away you've got an amine. Later on this semester, in the lab, you're going to identify unknowns. If an unknown happens to land in your lap that doesn't smell like dead fish, you don't have an amine. Okay, so just be aware. I tell students that every semester, and invariably, someone will spend 3 weeks trying to figure out what amine they have when they don't have an amine. Amines are a dead giveaway. They smell awful. All right. Another type of real diagnostic peak that we see in the infrared is the carbonyl peak. It's a carbon-oxygen double bond. Generally right around 1710 for a ketone, around 1725 for an aldehyde, and around 1710 for a carboxylic acid. Notice the difference in structure. We've not covered these in organic chems, but they each have a different generalized structure. The ketone is a carbonyl bond, but it's surrounded by other carbons on either side. That's the definition of a ketone. An aldehyde has a hydrogen in one of the positions, and a carboxylic acid has an alcohol. In fact, the carboxyl, the name carboxyl is a contraction of carbonyl and hydroxyl. Okay, because it's a blend of both types. Now, each of these share in common the carbonyl band, and so that will be present in all of them. It'll be the other things present that will allow you to distinguish between them. Okay? This guy, right here, there are two vibrational modes that can take place here, and it will vibrate around 27 or 28. In addition to the carbonyl stretch. By the way, the carbonyl stretch, the carbon-oxygen double bond, usually the most intense in the spectrum. Usually it serves as the base heat where everything else is normalized against it. Okay? These guys, in the aldehyde, will be much less intense. This will have nothing besides the carbonyl stretch. So the ketone will be just the carbonyl stretch, nothing else. The aldehyde will have this pair of peaks along with the carbonyl stretch. And the carboxylic acid will have the alcohol stretch superimposed on top of everything else. In general, the alcohol has, has a tendency to double bond more, or the carboxylic acid alcohol group has a tendency to double bond even more. We'll look at this as well in a moment. So it's real, these are usually real easy to identify. Here's the ketone. Here's my carbonyl stretch. And we don't see anything at 27 and 28. We don't see anything up here associated with an OH stretch that we might see with a carboxylic acid. One thing we often do see, and students will think it might have something to do with an alcohol, notice at 17, 18, that right up here, it should be about 34, 38, or 36. There's an overtone, twice frequency. Okay, and so you'll see a little bit of that on occasion. If the spectrum is kind of weak, it may just disappear into the background noise. But this is typical of a ketone. And again, notice the intensity of the carbonyl stretch, most intense in the spectrum. And what could you say about double bonds and single bonds here?
Okay.
All single bonds. There's no evidence of a carbon-hydrogen stretch above 3,000, so there's no evidence then of any double bonds in the backbone. Here's an aldehyde. Again, we see our carbonyl stretch about in the right region, but look at the 27, 28 band. Again, that has to do with that carbon-hydrogen on the end of the aldehyde chain, and there's two vibrational modes that give us a double peak. And it could be 2720 and 2820, it could be 2704 and 2804. But they're generally just 100 wave numbers apart and in that 27, 2800 range. If they're not there, you don't have an aldehyde. All right? Again, we have an intense peak here, there's an overtone out there. Here's the carboxylic acid. Here is the carbonyl stretch. Here is the OH stretch of the carboxylic acid. The carboxylic acid, here's one right here. Here's my OH and here's my double bond oxygen. Notice that these things hydrogen bond in a special way. They form dimers. They actually form a double hydrogen bond with their neighbors. And because of this increased strength of hydrogen bonding, the band is even wider and usually lower in energy. The hydrogen bond tends to shift things to the lower energy band a little bit. So this actually sort of falls on top of the other regular carbon-hydrogen stretches and often causes a lot of concern for students. You see this and you think, that looks awful. But in fact, that's real typical of a carboxylic acid. I said a lot of words there. Did you follow that?
Mm-hmm. It's going to confuse us because we're going to be looking at, we're going to be like, why is this alkane or thought at the time?
Yeah, you say, well, is this an alkane or is it an alcohol or is it an alkene? And everything is as it should be. Everything here, this is the carbohydrate.